Hi, welcome to another edition of Calculus 3. Today we are going to talk about velocity and acceleration. Mathematically speaking, this is very simple. Velocity is derivative of position, and acceleration is derivative of velocity with respect to time. Let's go ahead, take a look at the picture to make sure we understand the kind of algebra we are doing, and our progress is going to be rather quick in this section. So the idea is rather simple. So suppose we have a particle that is traveling in space. So the location of this particle can be given parametrically in terms of time. X could be equal to some formula, y is equal to another formula, z is equal to another formula, and the particle we are tracing it is at this location, as you see. As the time passes, the particle moves. You see I am animating this motion, and this is just going around. Okay, let's go to the beginning. We see two vectors. One is this black color vector. We are going to call it the velocity vector. Velocity as derivative of position. And then there is another vector, this green vector that you see here. Let me maybe move it a little bit further up. So the velocity is always tangent to the direction of the motion, and acceleration has a bit of a more complicated relationship with respect to the trajectory itself. If you are on a circle and you're going at a constant speed, your acceleration is going to be pointed toward the center of the circle, but in general it's going to be quite a bit complicated. We are going to talk about that later on. What we are going to do in this section is just to learn about the mechanics of the following. If I have the position, how do I find velocity and acceleration? And in reverse, if I have velocity, how do I find the position? Or if I have the acceleration, how do I find the velocity and the position? So let's go ahead and take a look at this simple issue. So we have a particle that is either in 2 dimensions or 3 dimensions. Actually, it could be 1 dimension as well. So let's go and take a look at the following. Suppose I have a particle just like what I showed you, and it is traveling in space. So while it is traveling in space is position, so we have a position typically shown by r of t. R of t is made out of 2 or 3 or perhaps even 1 quantity. So typically we have, say, x of t. If you were in just 1 dimension, that would be it. If you are in 2 dimensions, there's x of t and y of t. And if you are in 3 dimensions, well, you have all 3 of them. The other notation that is used is to write this x of t times the unit vector I plus y of t times the unit vector j plus z of t times the unit vector k, and I, j, k are the unit vectors we talked about. This notation is going to be a little bit more complicated for me to write, so I guess I'm going to stick to having them separated by a comma, and that's going to be simple. So that's the position. So what is meant by velocity? So if this particle moves at some time t so suppose this is start of the trip t, and then a moment later at the position at the time t plus delta t. So what is the displacement? Well, displacement is you have gone from this location to that location, and the way you write that is r of final position t plus delta t minus r of the starting position. Whatever that is, this difference is the displacement, and if you take it and divide it by delta t, well, that's going to be the average velocity from here to here. If you let this thing go to the limit as delta t goes to 0, what you recover is called written r prime or drdt, and it is simply the derivative of these three functions that you had. So I'm going to drop the letter t also to make it less crowded and more visible. So that is going to be our velocity. So the velocity depends how you are traveling on this path. If you change how quickly you go, of course your velocity is going to be different. Next to the concept of velocity, we have the concept of speed. Speed is the absolute value of velocity. So if you are going in one dimension, velocity could be positive or negative, but the speed would be just absolute value. So if in case it was negative, you erase the negative sign. In 2 or 3 dimension, it's going to be the absolute value of the vector. Absolute value of vector, you remember how to write that. Absolute value of vector is going to be the so-called norm of it. So it's just a Pythagorean theorem. You square them, add them up, take a square root, that would be like for hypotenuse, or the diagonal. So in this case you recover speed. Now in your textbook, the speed is going to be written by double absolute value sign or vertical bar sign. Again, that's going to be a little bit too crowded for me and makes my formulas hard to see and read. So I'm going to stick to one single absolute value. In many advanced texts do the same thing, just so that our formulas don't look so cluttered with so many pieces next to each other. So as far as I'm concerned, these two will be the same. And web sign and such, you be careful and use the whatever notation they are asking from you. So as we go around, of course, we have the velocity. So if I am going in on this path, velocity is going to stay as a vector that is tangent to this path. So if you want to find the tangent vector for a trajectory, easiest thing is to calculate the velocity, and that's going to be a vector that is tangent. Of course, once you have a tangent vector, if you take it and stretch it by any multiple, that's still a tangent vector, and any of them is as good as any other one. So here, so let's write tangent vector is any multiple of, a tangent vector is any multiple of r prime. So when you calculate the velocity, any multiple of that, so if I could multiply r prime by 2 or divide by 2 or anything, I will have a tangent vector. Among all of these things, one stands out, the unit tangent vector. So unit tangent vector this is a vector that we normalize it so that the length of it will be 1, whatever the notation, whatever the standard length is for us, we cut it down to size, and that's going to be our unit tangent vector. Unit tangent vector is going to there are going to be 2 of them, one going in one direction and the other one's going in the opposite direction, and one of them could be chosen by us. So if I take r prime and then divide it by its absolute value, I will get what is called a unit tangent vector, and the letter T is reserved for that. Next up is, of course, acceleration. You know from basic physics or calculus that the derivative of velocity is going to be acceleration. So it's very simple that if you have r prime, you just do another differentiation, and then you are going to have your acceleration. So in our notation, it's going to be x double prime, y double prime, and z double prime. So as simple as that, we have our acceleration. So again, let me remind you what we did here at the beginning. That was just a way of describing this. So this black vector was our tangent vector, and that's a velocity. This green one is acceleration. You can even ask for more than that if you want to actually see the position. You can ask for position. Now it's going to be a little bit crowded. Let's see if we move around, see if it gets any better. So this blue vector is my position. This is R. This black one is R prime. This green one is R double prime. So we are going to be playing with these things in a variety of ways, going back and forth between them. And then in the next section, we are going to have a rather challenging and conceptually much more advanced topic about curvature and topics like that. So, but right now our job is quite easy. So let's just do some basic examples. So very simple example. In this case, it doesn't really make any difference if you have 2 components or 3 components, all the same. So let's start with a simple example. Suppose a position is given to us as t and t squared plus 5. So there shouldn't be like a mystery to you. What is this thing? Remember, this is sitting in the position of x. This is sitting in the position of y. So what we are saying is that the y is equal to, what is it? Y is equal to x squared plus 5, is right? T squared plus 5, t is x, so y becomes x squared plus 5. So this is just your trusty parabola from middle school. You had a lot of encounter with this shape. What we are doing now, instead of just giving you the entire parabola all right off the bat, we are gradually building it up. That means at time 0 we are here, and a moment later we are here, and a moment later we are here, and so on. And if you back in time, if you play the movie back in time, we are going to go on this left side of it. Okay, so prior moment, maybe perhaps we were there, prior moment perhaps we were there, and so on. So this is simply a way of describing how to travel on that curve. At a certain speed we are traveling on that curve. Now here's the example. So find the velocity. Find velocity. Well, very simple. R prime is equal to derivative of this is 1, and derivative of that is just 2. So that's it. Suppose we say find speed. Well, of course, these things are functions of time. Speed is supposed to be absolute value of this, just the Pythagorean theorem. 1 plus square of that was the square of that, 4t squared. And so, what about acceleration? Acceleration, that's r double prime. R double prime, well, derivative of 1. What's the derivative of 1? Well, simply 0. Derivative of that was that? Well, derivative of that is 2. Let's even though I put it aside, let me push maybe some examples. Use this notation as well, just to remember what's going on here. So 0 means I don't have any component in the I direction, and 2 in J direction. So to make it remember, we said in your textbook they write these things in boldface, so it stands out. Some textbook puts the arrow on top of them just to say that these are vectors. So this is keeping to position of the first place, this is the second place, and so on. So that's my acceleration. The problem as short as sweet as that. Sometimes you go in reverse. Let's practice that. Suppose we know that the acceleration is given to us as, say, 2i plus, say, 6tj plus say 10k. Acceleration is given. So what we want to find is, well, what is the velocity and what is the position? That's what we want to find. So we have to do what we did here in reverse. Remember, when you go from a derivative back to the original function, you always have a constant to worry about. So if I integrate this thing, it's of course 2ti. What's the antiderivative of 6t? Remember, you're taking antiderivative. What's that? 3t squared. Is that right? J. Antiderivative of this thing is 10tk. Now comes the issue of constant. What is our constant? How do we write it? And what does our notation mean? Our constant now is a vector, or you have to either allocate a constant for each of them, or if you want to write your constant as a single entity, you have to remember it's a vector. So here I do two things. First of all, I make it bold, and second, I put an arrow on this to remind everybody this constant really has three baby constants in its belly. It is a constant for this one, a constant for this one, a constant for that one. And the alternative for writing it this way would be, so for example, you could have written 2t plus constant number 1, I, say 3t squared plus constant number 2, j, plus in this one is going to have its own constant, let's call it c3, j, k, excuse me, k. Okay, what is the meaning of C1, C2, C3? What are these things? Well, if an object starts rolling at the very beginning, it has a certain velocity. So that gives us a concept of initial velocity. Initial velocity is connected to what these constants are going to be. In this case, so we have a concept of initial velocity. We typically show it like v sub 0 or v at time 0 or something. So that's what we call initial velocity. So if we, for example, if you have a stone in our hand and we just drop it, then the initial velocity of that is 0. Anything that you just release and doesn't have any kind of momentum of its own, its initial velocity will be 0. Here, just for sake of example, suppose the initial velocity of this object is, say, just to make an example, say 2, 4, and 6. So that would mean that this is C. Well, here this is a velocity at time t. We go calculate what is it going to be at time 0, at initial time. It so happens that these functions that we have, I forgot to put a t here. These functions that we have in this case, incidentally, all of them become 0. That's just a coincidence here. And all that is surviving is C1, C2, and C3. If that is given to me to be 2, 4, 6, well, this is 2, that's 4, that's 6. So velocity at time t becomes 2t plus c1 I, and so on, 3t squared plus 4 j, and this was 10. Excuse me, I made a mistake here. This k is outside. We just have a t here. Sorry for that. So I have 10t, and c3 is 6 in this case, and it's just 1k outside. Okay, that's my vt. Suppose I want to get, so this is my velocity. How about my position? Position is going to be r of t. How do you get r? Well, r is the antiderivative of v. V is the derivative of r. So you have to take the integral of this thing one more time. So that in that case is going to be t squared plus 2t. Now another constant. Let's call it k1 I. And this is going to be, well, t cubed plus this is going to be 4t and some other constant, say j. And then here is going to be 5t squared plus 6t and a third constant. So who are K1, K2, K3? Well, they are all tied into the so-called initial position. Initial position, that's going to be R at time 0. So when you are releasing an object, you decide on two things: where to release it. Where to release it is initial position, and at what speed to release it, and that is going to be your initial velocity. Two things are under your control: initial position and initial velocity. Like if you want to throw a ball, you go to a certain place and that you throw the ball in a certain manner. Two things to decide. So suppose we have R0 or R at time 0, and let's make that to be nice numbers: 10, 20, and 30. So if I have such a thing as initial position, and given that the rest of these things at time 0, so at time 0 this thing becomes K1, K2, K3 in this case. You have to go and check really. Yeah, it's not always the case that these things become 0, but in this problem, since they are all polynomials, at time 0 they all just become 0. And so I am given some numbers for my initial position, and therefore I can recover my position. So t squared plus 2t plus 10, first entry. Let's go back to this position. T cubed plus what's that, 4t plus 20 for the second one, and this one became 5t squared plus 6t and say 30. That's a third component. So this is some kind of a curve in space. Not going to be easy to guess what it looks like, but it's just some curve. That is the trajectory of the particle that is undergoing such an acceleration, and with those initial position and initial velocity. One of the famous problems that you see in a variety of courses, you see in your physics and engineering and math classes, all of them, you notice at the point that they're all talking about the same thing. It looks like as if they copied each other. Well, because of the importance of the problem, it shows up everywhere, and the issue of projectiles, projectile motion is an approximation for how something is going to move near Earth. So presumably we have this Earth here, and well, maybe a little bit better than how I drew it, and you have some stone, and then you throw it, and it goes some direction and falls. So approximation for what reason? Approximation is, first of all, the problem can be quite complicated for several reasons. If you're far away from Earth and then throw your object, you essentially throw a satellite, and that is going to be under a variable force, and that problem becomes complicated for that. If you are around Earth and you actually throw an object, well, you have to worry about drag force of air and wind and so on. So we are making a very simplified description of this thing. The object is close to Earth, and there is no friction or there's no drag force, and the gravitational force is constant. So we are essentially looking at a rather rosy scenario of everything being very simple. One additional degree of simplification, let's suppose everything is falling inside nicely our coordinate system, say x and y. An object that we throw and there are no additional forces acting on it is going to stay in a plane, and that plane we are going to call it xy plane or ij plane. And so we take an object and throw it, and it's going to travel like this. So the object is traveling under the force of acceleration. This force of acceleration and the force under the simplification that we made, that first of all, you're close to Earth, so the gravitational force is not changing that much, and second, there is no air resistance and such, we can write it as mg, which is the weight of the object, and since in the direction of the y-axis, the direction now is going to be called j, and since pointing downward, this is going to be, well, that's going to be the force minus mgj. Okay, this j here is just your unit vector. You remember from your physics class that F is equal to what? What was Newton's law? One of the more famous laws in beginning science. F is equal to, yes, everybody who has watched any science fiction movie knows F is equal to ma. So that means a, so ma is equal to that, means acceleration has to be equal to minus gj. Okay, it's the acceleration in negative y direction. Okay, then what? Well, the velocity is going to be antiderivative of this thing, so I have to take a antiderivative, becomes minus g t j plus some initial velocity, let's call it initial velocity v sub 0 for a moment. And then what? And then the position. Well, position, I have to take another antiderivative. What's the antiderivative of t? Minus g t squared over 2j, and this is a constant v0. Antiderivative, you just multiply by a t, and then you have an initial position. Initial position is going to be r sub 0. So this is a kind of a formula you see in your beginning physics or some mechanics class. That mysterious t squared over 2, you might be wondering where is the 2 coming from, why is that? Well, very simple. You take antiderivative, another antiderivative, and that gives birth to this 2, and that g is of course your constant of acceleration. Now how about this v0? How do various problems talk about v0? Remember we said v0 was the initial velocity. Initial velocity sometimes is expressed in terms of initial speed and angle. Like I might say, I'm at this location, I am throwing something at some angle, so I might say I'm throwing something at say 40 degrees at the speed of let's say at the speed of, I don't know, 10 miles per hour or something. So if that's my speed and this is my angle, how do I get my velocity? Velocity is simply equal to whatever speed you have. Remember, speed was absolute value of this thing times, well, it has two components, one in x direction, one in the y direction. X direction is going to be this times cosine of this angle, so that is cosine of whatever angle they gave to us. Let's call it theta. That's cosine of theta, say I, and then in the vertical component that's going to be sine of theta, and that's going to be j. So that is going to give us a unit vector in this direction. When you multiply by my speed, I'm going to get my velocity. So my initial velocity is going to be the initial speed times cosine of the angle with respect to the horizon at which it travels times I, and sine of theta times j. How about r0? Well, r0 is going to be initial position. Initial position, usually they specify for you, maybe there's some building, you're going on top of that building. Well, the initial position is going to be the coordinate of that location. Perhaps you extend your like you're on the roof of a building, you have some y location, some x location, so that is some pair of numbers that specify your initial position. So all in all, r becomes minus 1/2 of g t squared j plus initial speed times the angle at which you throw it. You take a cosine times I in sine times j, these are I and j, And then we have some initial position as well. If you want to write it in this notation, it's going to be hi plus kj. So hi would be like the height of the building, and k is going to be your lateral movement that you have. Now you can of course collect all of the i's together, all the j's together, but I think I prefer to leave it like this and call it a day and say this is our position. So the projectile problem, it's best to understand all the components as opposed to trying to memorize a formula. There's really nothing here to memorize, and that is going to give you your position. Okay, so this section is rather simple and sweet, but the problems do become complicated as soon as we add some new twist to the story. So you want to make sure you are up to speed with respect to this, and it is second nature to you, so that we are ready for the next one. Okay, so until the next lecture, good luck and God bless.